today, or I am Setran Daniels, a fellow member of the A Team, which is a group of analytical chemists from the University of Johannesburg. In this video, we will be discussing the removal of cadmium-2 from water. Clean water resources are vital in our everyday lives. The major problem that has presented itself is contamination due to heavy metals. This one in particular being cadmium-2 contamination. Cadmium-2 is not usable within the various industries and is also very toxic, carcinogenic, thus ultimately endangering the lives of both flora and fauna alike. Fortunately, our fellow analytical chemists have discovered a method to reduce the cadmium content within our water resources through the use of carbon nanodots embedded on various types of membranes.
To present methods on synthesizing carbon nanodots and producing advanced membranes using the phase inversion method. Phase inversion method is a popular technique for fabricating membranes, particularly for water treatment and separation applications. It is a process where a homogeneous polymer solution undergoes a phase transition, resulting in a formation of a porous membrane. Material sourcing. Whole grain oats were sourced, specifically jungle oats, for their sustainability. Essential chemicals like PES, PVP, and NMP were obtained from Sigma Aldrich, while electrodes came from BASI. CND synthesis. To synthesize CNDs, grams of oats were pyrolyzed at high heat, resulting in a black product that was crushed, purified through centrifugation, and dried, yielding a stable aqueous suspension of CNDs. Membrane fabrication. For membrane fabrication, phase inversion technique was used. CNDs were mixed with NMP sonicated and combined with PES and PVP to form a casting solution. This was cast onto glass plates and submerged into a coagulation bath of water for solidification. A secondary purification step removed residual NMP, resulting in a ready-to-use membranes.
Variability in composition. An important aspect of this method is the ability to adjust the membrane composition based on the percentages of CNDs, allowing for tailored properties for various applications. In this process, we highlight the commitment to sustainable innovation in material science. The benefits of the methods utilized above is ensuring strong interactions between CNDs and PEs, potentially improving adsorption efficiency, and to allow for precise control over the thickness and distribution of CNDs, which optimizes membrane properties for enhancing cadmium ion adsorption. This also includes the improvement of surface area available for cadmium adsorption, which enhances electrical conductivity and adsorption capacity, making it effective for metal ion removal.
Results are as follows. Through rigorous characterization, the conformation of the membrane's durability and hydrophilicity were enhanced by the carbon nanodots or CNDs. FTIR spectroscopy analysis revealed characteristic peaks of OH and COO functional groups present in the CND. SEM imaging confirmed the existence of these CNDs on the membrane surface. It was taken a step further by testing the membrane on drill water supplies. The ICP-OES analysis confirmed 58.38% of cadmium was removed from spiked tap water. Through this experiment, it was found that the higher the carbon nanodot content, the more cadmium was removed from water.
TEM displayed sufficiently scattered and spherical carbon nanodots with uniformly shaped structures averaging sizes of 6.7 to 2.8 nanometers, therefore maximizing surface area for interaction with contaminants. The FTIR confirmed that the combination of PES with the CNDs by an introduction of a new functional group at 3,400 centimeters, which was attributed to the hydroxyl group due to the presence of CNDs. This increases the hydrophilicity of the PES membrane, which further allows the membrane to interact better with water molecules, possibly even improving its filtration properties and allowing for better adsorption of cadmium 2 ions from the contaminated water. The larger amount of CNDs coated on the PES decreased the contact angle, improving the hydrophilicity of the membrane, making it more attractive to water. This enhancement in hydrophilicity can be related to the presence of hydrophilic functional groups, example being the hydroxyl and the carbonyl groups found in the CNDs, as reported in the FTIR analysis data shown during the water flux, which indicated that an increase in proportion to the CND's concentration in the membrane. In conclusion, this study demonstrates significant promise for real-world applications such as providing assistance to water treatment facilities with heavy metal contamination, particularly in the industrial regions. The experimental results show that these nanobots increase the membrane's filtration efficiency, removing more cadmium. By integrating these CNDs into existing filtration systems, we can remarkably improve the water quality and safety, contributing greatly to the public health sector.
Special thanks to Professor Mabuba and Professor Malinga, along with the chemist from the Environmental Research and Public Health Group, and our fellow group members for their invaluable contribution and teamwork towards this presentation.